യെസ് സ്റ്റാർട്ട് ചെയ്തു.
Okay. Good evening, one and all. I feel privileged to extend my warm welcome to all present here. We have all gathered today to be enlightened by certain brilliant projects that our adoring seniors submitted with all of their talents. Let me wholeheartedly welcome to all of you to the UG Project Presentation 2022-2021. First, let me welcome Sonal Preet for the prayer.
കാണായ ലോകങ്ങൾ കാക്കുന്ന ദേവ കാരുണ്യ സിന്ധോ നമിക്കുന്നു നിന്നെ കരളിന്റെ പൂക്കൾ നിൻ പാദതാരിൽ കാണിക്ക വെച്ചോ നമിക്കുന്നു നിന്നെ കാണായ ലോകങ്ങൾ കാക്കുന്ന ദേവ കാരുണ്യ സിന്ധു നമിക്കുന്നു നിന്നെ കരളിന്റെ പൂക്കൾ നിൻ പാദതാരിൽ കാണിക്ക വെച്ചോ നമിക്കുന്നു നിന്നെ ലോക സമസ്ത സുഖിനോ ഭവന്തു ഈ മന്ത്രമീ ലോകമെന്നും മുഴങ്ങാൻ വിജ്ഞാനദീപം നിറകത ചൂടാൻ നേരിന്റെ പാത തെളിക്കണമേ നീ.
Let me invite Abhijaya for welcome speech.
Yes, Abhijaya.
Stay to one and present. It's privilege to be here welcoming you to this program, UG Project Presentation 2020. First, let's welcome Ms. Aishwarya for Department of Mathematics. Welcome.
Thank you, Abhijaya.
Next, I welcome all others here. Let me welcome the project presenters of today's program. I welcome Aishwarya, Yama, Nayantara, their project topic Stimulation atmospheric parameters using Python. Sita Lakshmi Thomas on
അബ്ജയ എനിക്ക് മുറിഞ്ഞാണ് കേൾക്കുന്നത്. കുറച്ചുകൂടെ റേഞ്ച് ഉള്ള സ്ഥലത്ത് നിൽക്കാമോ? ഇപ്പോഴും ഒരു ചെറിയ പ്രശ്നമുണ്ട്. Better ആണ് അബ്ജയ. Carry on.
Let me welcome the project presenters of today's program. Please welcome Aisha, Liana Fatima, Nayantara, presenting their project topic, Basic Atmosphere Meeting. Sita Lakshmi Rita Thomas on Fractal Geometry and C. Maria K.S. and on estimation of the outbreak of universal pandemic. Small. Last but let me no friend here. Thank you.
Thank you, Abhijaya. Now I invited Ms. Aishwarya Paul for the presidential address.
Thank you, Nafeda. Respected chief guests of the day. We indeed have so many chief guests here. My dearest former students, Fida, Liana, Nayantara, Ria, Sita Lakshmi, Vibha, and Simi. Dear teachers and all my dear little ones. I'm indeed very much delighted to have 7 of you back here to inspire your juniors. These 3 projects, these 3 were the best projects that I could find out in the past 2 years. So that is why I have invited these these seven best students, I can say, to inspire you all, so that in the coming year you become more motivated to present a project like this to your juniors. These three projects, the first one, stimulation of basic atmospheric parameters using Python. It was done by Fida, Liana, and Nayanthara. This was a kind of a different project, that is, it has the base of physics in it, but they used Python, that is a language in computer, which is very closely related to mathematics, to do the project. Second project, fractal geometry. Fractal geometry is usually taken by all the batches, but I could see that this batch, Ria, Sita Lakshmi, and one more person was there, right, Ria?
Yes,
Sandriana.
ma'am, Sandra.
Yes, yes. Okay, these three done it very well. They included applications of fractal geometry in it, and they presented it in a very, very pleasing way. The third one was the estimation of the outbreak of universal pandemics done by Simi and Vipa. These two usually, they are updated to the present situation always, and ആദ്യം തന്നെ നമ്മൾ പ്രോജക്റ്റ് തുടങ്ങുന്ന സമയത്ത് തന്നെ they wanted to take something related to COVID-19 pandemic. So I found these three projects very interesting and very useful for the coming juniors also. And you should have seen the work they did, the hard work they did to do the project, for the editing that they did, and for the presentation of the project also. They did it in a very professional way, that they had their own contributions in it, and that is the reason they were selected to give you guys an overview of how you have to do a project. I hope this presentation motivates you guys. And from the bottom of my heart, I genuinely hope that you all come up as chief guests for better and bigger opportunities. ഞാൻ ഈ ബാച്ചിനെ പറ്റി എന്തായാലും പറയണം. സച്ച് എൻ എനർജറ്റിക് ബാച്ച്. എപ്പോഴും നമുക്ക് സർപ്രൈസസ് തന്നുകൊണ്ടിരുന്ന ഒരു ബാച്ചായിരുന്നു. എനിക്ക് ഇവർക്ക് ഞാൻ കൊടുത്ത ഒരു പ്രോമിസ് മാത്രം എനിക്ക് നിറവേറ്റാൻ പറ്റിയില്ല. ഇവരെ ടൂർ കൊണ്ടുപോകുമെന്ന് ഞാൻ പറഞ്ഞിട്ടുണ്ടായിരുന്നു, പക്ഷെ അതെനിക്ക് ചെയ്യാൻ പറ്റിയില്ല. ദാറ്റ് ഇസ് ബിക്കോസ് ഓഫ് ദിസ് COVID-19 പാൻഡമിക് ഓൺലി. അതർവൈസ് ഐ വുഡ് ഹാവ് ടേക്കൺ യു ഫോർ എ കോളേജ് ടൂർ. എനിവേ, ഓൾ ദ ബെസ്റ്റ് ടു യു ഓൾ, ആൻഡ് കം ഔട്ട് ഇൻ ഫ്ലൈയിങ് കളേഴ്സ്. താങ്ക് യു.
Thank you, ma'am. Now let us move on the main content of today's program. I welcome Aisha, Fida, Liana, Fatima, and Nayandara for their presentation.
ഹലോ മാം, ഓഡിബിൾ അല്ലേ?
നയൻതാര ഓഡിബിൾ ആണ്.
പ്രസന്റ് ചെയ്തോട്ടെ.
യെസ്, ഓഫ് കോഴ്സ്.
മാം കാണാൻ പറ്റുന്നുണ്ടോ?
അത് യെസ് കാണാം കേട്ടോ.
Good evening, one and all. Today we are here to present our project titled Simulation of Basic Atmospheric Parameters using Python. As you can see, there are three main words in the title: simulation, atmospheric parameters, and Python. At first, we are going to look after what is atmosphere and what are its parameters. Atmosphere, it is a set of layers of gases surrounding by a planet or other material body that is held in place by gravity of that body. Our Earth also has an atmosphere which is entirely different from all other planets in the universe, because Earth has the presence of life in it. So its atmosphere is entirely different. It has a significant role in shaping lives on Earth. It helps for weather formation, climate change, maintenance of medium temperature on Earth, and so on. Also, Earth's atmosphere extends up to 10,000 kilometers from the surface, and it has a mass of about 5.15 into 10 raised to 18 kilogram. And the term atmosphere is a Greek word which is derived from the Greek words atmos, which means vapor, and spharia, which means sphere. And the composition of atmospheric gases in percentage is given in this pie chart. Here we can see the element nitrogen. Nitrogen gas is present 78 percentage, and oxygen 21 percentage, and argon 1 percentage, and 1 percentage of other gases. Also, when we look after the other gases which are present in atmosphere, we can see there are water vapor. There is greenhouse gases which include carbon dioxide, methane, nitrous oxide, which causes the greenhouse effect, which makes earth comfortable for living, and also the very important ozone layer which protects us from the UV radiations coming from the sun. And all these are included in the atmosphere. And atmosphere is divided into five main layers, which is based on the characteristics such as the temperature, the composition of these gases, etc. And the five main layers are troposphere, stratosphere, mesosphere, thermosphere, and exosphere. We are not going into detail of these five layers. Next, I should introduce the atmospheric parameters. The first atmospheric parameter is the atmospheric pressure. Atmospheric pressure in a particular location is a force per unit area within the atmosphere. That is, when we measure the pressure at a certain location, it is a force per unit area in that location. And pressure at sea level is known as a barometric pressure, and its value is 101325 Pascal. So we are going to look about the variation of pressure with altitude. As altitude increases, pressure decreases. That is the relationship between them. It is because of the gravitational pull of Earth. Because when altitude increases, the molecules become far away from each other, and the pressure decreases. Molecules are close together at the surface of Earth than from a height from the surface of Earth. So the variation of pressure with height vertically can be approximated by the formula P equal to P naught e raised to minus h by h, where small h is a height at which we have the pressure capital P, and P naught is the pressure at sea level, and capital H is a scale height which is a constant. And the next atmospheric parameter is atmospheric density. Density of air is a mass per unit volume of Earth's atmosphere. It changes with the variation in atmospheric pressure, temperature, humidity, etc. As we seen in earlier, in the case of pressure, density also decreases with increase in height. The density close to ground is given by the formula rho naught is equal to P naught m by R into T naught. Rho is a symbol that we use to denote density. So rho naught is a constant, that is density close to ground is a constant, which is given by P naught into m by R into T naught, where P naught is the pressure at sea level, m is a molar mass, R is a universal gas constant, and T naught is a temperature at sea level. And next, the approximation of density, exponential approximation of density with altitude is the formula given by rho equal to rho naught e raised to minus h by h, where rho is the density at the height small h, and rho naught is a ground level density, and capital H is a scale height. Now we are moving to the section known as atmospheric waves, which is also an important one. And now I welcome Aisha Fida for taking over that section. Thank you.
ഹലോ കേൾക്കുന്നുണ്ടോ?
കേൾക്കാം.
Yes, yes.
Okay. Okay, then here I taking the portion atmospheric waves. Atmospheric waves a periodic disturbance in the field of atmospheric variables like surface pressure, geopotential height, temperature, and wind velocity. And this periodic disturbance, which may either propagating dynamic disturbance of one or more quantities, traveling wave, or which a wave oscillates in time, standing wave. Atmospheric waves are the fluctuating motion of the neutral air in the terrestrial atmosphere. And this atmospheric into three main groups: planetary waves, tides, and gravity waves. Rossby waves are planetary waves. They are very long frequency waves, and they are naturally occur in the rotating fluids of the Earth. And gravity waves are the local and regional waves. These waves are classified on the basis of propagation of wave caused by the imbalance of the forces acting on the air very latitudinally, principally because of the Coriolis effect. And these waves is mainly excited in the troposphere and stratosphere and propagates vertically and also horizontally. While propagating, this wave will transport energy and momentum from their source regions across the atmosphere and will be able to dissipate under special circumstances. Then gravity waves. Gravity waves is generated in a fluid media or at the interface between the two media when the force of gravity or buoyancy tries to restore the equilibrium. Drop a stone into a pool of water. The spreading ripples are gravity waves. Gravity or buoyancy is a restoring force, hence the term gravity waves. And gravity waves can only exist in a stable stratified atmosphere. The gravity waves on an air-sea interface of the ocean is called surface gravity waves. Gravity waves within the body of water is called atmospheric internal waves. And these atmospheric internal waves are occurring when a uniform layer of air blows over a large obstacle like a mountain or a island. And gravity waves and the difference between the gravity waves and the atmospheric internal waves are the atmospheric internal waves are occur between the layers of atmosphere with the different densities, and the gravity waves are occur layer of atmosphere. Gravity waves do more than give clouds interesting shapes. In a upward moving region is the most favorable region for the cloud development, and the sinking region is the most favorable region for clear sky. Due to this reason, we can see that clear areas between the rows of clouds. In Earth atmosphere, gravity waves are mechanisms that produce a transfer of momentum from the troposphere and stratosphere and mesosphere. The gravity waves are generated in troposphere and by the frontal systems, and thunderstorm updrafts will produce gravity waves as a try to punch into tropopause. And the trigger mechanisms will generate gravity waves within the clouds trying to push into tropopause. The examples of trigger mechanisms to produce gravity waves are mountains and thunderstorms. Their vital role in the transferring energy, momentum, and chemical species between the different atmospheric layers, and in the subsequent influence on upper atmospheric winds, turbulence, and temperature. Now I invite Liana for taking the portion.
Hello, ma'am. Is it audible?
Yes, Liana.
Yeah. So you have heard about atmospheric and basic atmospheric parameters. So our topic is to simulate the atmospheric basic parameters. So here for that we use the tool, programming tool Python. So first let us introduce the tool Python. Python is a programming language created by Guido van Rossum, and it is simple to use and free to install on Windows. The peculiarity is that Python can be freely installed on your system without the help of any technicians, and it works based on the input given into the program written. So codes used to write are short statements, not at all lengthier, that defines or mentions the parameters connected to result. The thing is that since these codes are so shorter, you can remember and use very without forgetting. These codes are easy to write and remember according to the expected result. Programming codes change according to our aim of expected results. So Python has its name. Python is known as a readable language because comparing to other programs, Python uses the language English, and also it is visually its format is visually uncluttered. That means the format is very neatly arranged. The codes and arrangements in Python software is very neatly arranged. So it is known as visually uncluttered and readable programming language compared to other programming softwares. And also uh, Python also has the name cross-platform because it can be installed on Mac, or Windows, or any system you have. You can use it. So it also has the name cross-platform. Also, it has the name large standard library because Python includes Python includes every like packages, softwares, anything that you need. So it is known as large. Sorry, ma'am, I got an inconvenience.
Can't
Now
you
is it
continue
audible?
it? Yes, yes.
Okay. So next you can see this Anaconda home screen here. After installing the Anaconda home Python software, the first page is you can see is Anaconda home screen. Here you can see various platforms like Prompt, Jupyter Lab, Jupyter Notebook, and Spider. So now let us take Jupyter Notebook. Here, when we take this Jupyter Notebook, you can see the numerical calculations, and these output are got by clicking the option run, and also the statements like hello world all are written as it is. Next, a spider home screen. It is another software in Anaconda home screen. There you can see two sections. The left section is the blank space where you write programs, and the right section is where you get the plots or the results. Here you can see as an example of a graphical plot, as programs are written in left side and plots are in right side. So our next chapter is simulation of basic atmospheric parameters. So we have seen about atmospheric parameters, density and pressure. So first let us talk about density profile. So in density, we have learned that density decreases when height increases due to low gravitational pull at points farther from Earth's surface. As we go higher from Earth's surface, density decreases as because number of air molecules is less. So we have learned the equation rho equal to rho 0 e raised to minus h by h. And using this single equation, we are going to plot the graph using the program Python. Here you can see this atmospheric density profile, density and altitude. Here you can see that all as altitude decreases, this density got decreasing. It is an inverse relation. With the single equation rho equal to rho 0 e raised to minus h by h, we have created the plot atmospheric density profile here. Next, pressure profile. So pressure profile also is an inverse relation, P equal to P0 e raised to minus h by h. Higher the altitude, lower the pressure. So this variation also we have plotted using the Python program, pressure profile. Here also you can see the pressure increases over the right side from low pressure area to higher pressure area as altitude decreases. So with this single equation, we have plotted the variation, inverse relation using some programs and using Python. So I next invite Fida for the rest.
Atmospheric waves, amplitude vs altitude. Amplitude is the maximum displacement.
Yes, കേൾക്കുന്നുണ്ട്. പറഞ്ഞു.
Atmospheric waves, amplitude vs altitude. Amplitude is the maximum displacement or the distance moved by a point on a wave measured from its equilibrium position. Amplitude of a wave increases with altitude to compensate the energy loss occurring while density becomes lower with altitude. We know what is wavelength. Wavelength is the distance between the two waves, and the amplitude is the maximum displacement. And the energy formula of waves in atmosphere is given by E is equal to 1 by 2 rho square A, where rho is the density at a height h and a is the amplitude of the gravity wave. From this formula, the amplitude a is derived, a is equal to 2e divided by rho square. This is a variation between the amplitude and the altitude. We can see that amplitude and the altitude are directly proportional. Then gravity waves. We know that the law of conservation of energy, energy neither be created or nor be destroyed. The general formula for energy of atmospheric waves is given by E is equal to 1 by 2 rho square A, and the vertical propagation of the gravity waves with the increase in amplitude can be plotted using the formula A sine omega z. This is the vertical propagation of the gravity waves and the variation between the amplitude and height, and this is the horizontal propagation of the gravity waves, variation between the height and amplitude. We can see the difference between the vertical propagation of gravity waves and the horizontal propagation of gravity waves. Now I invite Nayandara for taking the portion vertical and horizontal propagation of gravity waves with constant frequencies.
Naintara, we can't hear you.
ഹലോ
ആ ഇപ്പൊ കേൾക്കാം.
നേരത്തെ കേട്ടില്ല.
ഇപ്പൊ പറഞ്ഞത് ഒന്നും ഇല്ല.
Okay, ma'am. Next, we are going to see how the vertical propagation of gravity waves vary as we change the frequencies while setting the energies constant and while varying the energy by setting the frequency constant. This is a diagram with frequency is equal to 20. And when we observe, we can see the waves are so closer such that we cannot distinguish one from the other. And when we set frequency as 30, it becomes some more closer, that is some more congested. And then we set frequency as 50. So as we observe these three graphs, we can see that as frequency increases, each wave becomes very close to each other and they are so adjacent. So the number of waves per unit time in this graph increases. This is a comparison with frequency that we do in the vertical propagation of gravity waves. So we cannot distinguish each line from the other. When we decrease the frequency to omega equal to 4, we can see the difference very clearly. That is, omega equal to 50 is like this and omega equal to 4 is like this. So the number of waves per unit time increases as frequency increases. So the next one is, by setting frequency constant, we are varying the energy. This is a graph with energy equal to 50 joule. In this graph, we can see that the wave has a higher wavelength at lower heights, but it doesn't travel the it doesn't travel more altitude, because it gets dissipated because it has a low energy. So when energy is low, we already know that when energy is less, it does not travel a higher height. Its speed is also low, but its altitude is high in lower heights. When energy becomes 200 joule, we can see that the wave travels in more speed than the previous one. That is, the wavelength increases as height increases. That is, it travels the same height with a stronger manner. That is, its energy has increased, so its speed has also increased. And when energy becomes 2000 joule, we can see that more energy has come out and the wave is just bursting out as a rocket. So when we compare it with previous one, we can see the wavelength has decreased in that height, but it travels more height with more energy. So its wavelength is comparatively, its wavelength is very short to the previous ones. So it is stronger than the previous 50 joule energy and 200 joule energy waves. So the comparison can be easily recognized from these three graphs. So as energy increases, amplitude decreases, we can see from these three graphs. So this is a comparison of vertical propagation of gravity waves with frequency and with energy. Next, we are concluding our project. So in this project, we have stepped into learning a new concept, that is a programming language. Python is a versatile programming language which is a very powerful one, which has varieties of utilities in many fields, which include the current popular world of data science. So we have here familiarized about what is atmosphere and what is atmospheric parameters. We have studied the relationship between them and the altitude, and then we familiarized what is Python program. We have studied Python program using one online course in Udemy app. The course name was Data Science uh, was its name. And then we simulated the exponential variation of these atmospheric parameters using the Python tool. So we can see Python is a simple syntax and easy to learn, and it is easy to handle, and it is so free also. Uh, we can explore the higher level applications of Python in maths through this. This is only a first step to Python. So it has many opportunities and in the world of data science. So we have tried to explore a few of them. So that's all our project, and these are the references that we have used for completing it. And then thank you everyone for listening to us, and thank you, ma'am, for giving us an opportunity to present our project before our juniors. Thank you all.
Thank you, Aisha, Fida, Liana, Fatima, and Naindara. Now I invite Sri Lakshmi and Ria Thomas for their presentation.
Hello, ma'am.
Yes, Sita.
Hi, all. Our project is on the topic fractal geometry. A fractal geometry is a new branch of mathematics and arts. A fractal is a self-similar subset of Euclidean space whose
Fractal dimension strictly exceeds its topological dimension. Most physical systems in nature and human artifacts are not in regular geometric shapes and standard geometry of Euclid. A fractal means a curve or a geometrical figure. Each part shares same statistical characters as the whole. It is based on the idea cell-similar forms. To be a cell-similar, a shape must able to divide into parts that are small copies of which are more or less similar to the whole. All fractals are cell-similar. Not all similar forms are fractals. Fractals began to take up shape in 17th century. The, the first definition of fractals was definition of a function represented by Carl Weierstrass on 18th July 1872. In 1883, George Cantor introduced Cantor sets. Felix Klein and Henry Poincare introduced self-inverse self-inverse fractals. In 1904, Held von Koch introduced Koch snowflake. In 1915, Vaclav Sierpinski introduced Sierpinski triangle. In 1960s, Benet Mandelbrot started writing about cell similarity. Levio Fry Richardson later built statistically cell similarity and fractal dimensions. Next, definition and properties of fractals. Definition of fractal geometry is it is a branch of mathematics concerned with irregular patterns made of parts that are same in way of similar similar to the whole. There is a property that is cell similarity. A geometric figure is cell similar if there exists a point where every neighborhood of the point contains a copy of entire image. There are three types of cell similarity. Exact cell similarity. It is the strongest cell similarity. The fractal appears identical at different scales. Fractals defined by iterated function system often display exact cell similarity. Next one is quasi-cell similarity. It is the loose form of cell similarity. The fractals appears approximately identical at different scales. It contains smaller copies of the entire fractals in disordered and degenerated forms. The last one is statistical cell similarity. It is the weakest cell similarity that repeats a pattern stochastically. Random fractals are examples for this cell similarity. Next one is types of dimensions. Fra- Fractal dimension. It is the measure of how complicated a cell similar figure is in a rough sense, which measures how many points lie in a given set. It doesn't have to be an integer. Next we are in next calculation of fractal dimension. If we break a line segment into four cell-similar equal parts and each of magnified by a factor 4, then we get a original line segment. Here 4 is the magnification factor. Similarly, if we break the line segment into 7 equal parts, then 7 is the magnification factor. But in the case of cubes, it is different. Here we have an equation for finding fractal dimension, that is log n by log 1 by epsilon. Here n is the number of cell similar pieces and 1 by epsilon is the magnification factor. Epsilon is equal to the size of the original pieces to the size of the new pieces produced. There is another method, that is box counting dimension. Let f is the subset of R such that f is non-empty and bounded. Let n gamma of f be the smallest number of sets with diameter gamma needed to cover f. If the two are equal, then we get the box counting dimension. Last, there is two common techniques for generating fractals. First one is iterated function system. Iterated function system were introduced in 1981 by John E. Hutchinson. It works by applying the linear transformation again and again to the original set. It is useful when dealing with similar fractals. Examples, Koch snowflake and Cantor sets. The last one is escape time interval, escape time fractals. Fractals generated by means of escape time. Algorithms are computed repeatedly by applying a transformation to a given point in the plane. The obtained series of transformed points is, is called the orbit of the initial point. Here, example for this is Mandelbrot set. Now I am inviting Ria for presenting next part.
Good evening. So I hope you got a basic idea of what a fractal geometry is. Now to understand it further, let's go through some examples of geometric fractals. So first we have the Cantor set. So I hope it's visible and audible to you all. Ma'am, is it
Yes,
visible?
yes, Ria. Please
So
continue.
first we have the Cantor set. Cantor set is actually one of the basic examples of fractal geometry. I think you study it in the fifth semester also. So Cantor set was found out by George Cantor in 1883. The Cantor set plays a very important role in fractal geometry. To create a Cantor set, we start with a closed interval 0, 1. That is a line of unit length. That will be the first line that you see in the figure. Now we will divide the line of unit length into three equal parts. Then we'll have the points 0 to 1 by 3, 1 by 3 to 2 by 3, 2 by 3 to 1. Now we'll remove the middle open interval. That is the open interval 1 by 3, 2 by 3 will be removed. And we get the next iteration, that is the next line you can see in the figure. So these two line segments represent the closed interval 0, 1 by 3 and 2 by 3, 1. Let it be F1. Now we continue the iteration the same way, that is we take the closed interval 0, 1 by 3 and again divide it into three equal parts and remove the middle open interval. The same process we do to the closed interval 2 by 3, 1. We divide into three equal parts and take out the middle open interval. Like that we get F2. We continue the iteration up to Fn, and at n we get Fn will be the union of 2 raised to n closed interval, each of the form closed k divided by 3 raised to n, comma k plus 1 divided by 3 raised to n. Each interval is of length 1 divided by 3 raised to n. Hence we have the formal definition for Cantor set, that is the Cantor set is the intersection of the set Fn for n belongs to set of natural number obtained by the successive removal of the open middle third starting with the closed interval 0, 1. Now let's see some of the properties of Cantor set. So the first property of the Cantor set is that the total length of the removed intervals will be 1. And the Cantor set does not contain any open intervals. That is, if you take F1 or F2 or up to Fn, we can see all of them will be the union of closed intervals. There will be no open interval. Now the dimension, the fractal dimension of Cantor set is actually 0.631, which we get by the fractal dimension formula d is equal to log n divided by log 1 by epsilon. Next is the Koch snowflake. Koch snowflake was founded by a Swedish mathematician Helge von Koch in 1904. We construct the Koch snowflake by taking an equilateral triangle. You can see it in the stage 0, that is the initial stage. In this we can see an equilateral triangle of unit side length. So we take one side which is of length 1, and we divide into three equal parts, and we replace the middle part by the other two sides of an equilateral triangle. So you can see a small kink that is formed in each side of that bigger equilateral triangle. Like that we have three kinks. So in stage 1, if we take one side, initially in stage 0 we had the side length to be 1. In stage 1 we can see one side got divided into 4 smaller segments. Each segment has length 1 by 3. So we have 4 line segments, so it will be 4 into 1 by 3, that is 4 by 3. Like that we have 3 sides, so 3 into 4 by 3. In stage 2 it will be 3 into 4 by 3 into 4 by 3. In stage 3 it will be 3 into 4 by 3 into 4 by 3, and so on it continues up to n. We have 3 into 4 by 3 whole raised to n, which goes to infinity as n extends to infinity. Hence the perimeter, it has infinite length. Next, the area. We know an equilateral triangle of side A will have area root 3 by 4 A square. So in state 0, the equilateral triangle will have area root 3 by 4 A square, where A is the side length. In stage 1, we can see an extra 3 smaller equilateral triangles are also formed. So the total area would be root 3 by 4 A square, which is the area of the bigger equilateral triangle, plus 3 into, since there are 3 small equilateral triangle, it will be 3 into root 3 by 4 A divided by 3 whole square, and it repeats on up to n. When we take n iteration, the total area becomes root 3 by 4 A square into 1 plus summation up to n 3 into 4 raised to k minus 1 divided by 9 raised to k. Up to infinity, we will have the total area up to infinity. We'll have the area to be 2 into root 3 by 5 A square, and the dimension of the coach snowflake will be 1.262. Next, we have the Sierpinski's triangle or Sierpinski's gasket, or it is also known as Sierpinski's sieve, which is actually a fractal attractive fixed set with the overall shape of an equilateral triangle, which is subdivided into smaller equilateral triangle. We start with a filled equilateral triangle, each of side length 1, and then we subdivided it into 4 congruent equilateral triangles. And we invert the middle triangle 180 degrees and then take out the middle open triangle. Hence, we get 3 filled triangles, and we repeat the process again and again. And after kth iteration, we will have 3 raised to k triangles, each of side length 1 divided by 2 raised to k. So the total area would be 3 divided by 4 all raised to k, which extends to 0 as k extends to infinity. So the total area will be 0. Now to find the perimeter, we know there will be 3 raised to k triangles, each of side length 1 divided by 2 raised to k. So the total perimeter length would be 3 raised to k into 3 into 2 raised to minus k, which goes to infinity as k extends to infinity. So the perimeter length will be infinite. And the dimension of the Sierpinski's triangle is 1.585. Next, we have the Pythagorean tree. The Pythagorean tree is actually a plane fractal constructed from squares. It was invented by Albert E. Boschmann in 1942. So he created the Pythagorean tree by taking a square and then placing another 2 square on top of it, such that a small triangle is formed in between, as you can see in the figure, each scaled down by a linear factor root 2 by 2. Since there is a triangle formed in the middle, it is actually a triangle that depicts the Pythagorean theorem a square plus b square is equal to c square. That's why it gets its name Pythagorean tree. Now we keep on adding squares on top of squares until we get a Pythagorean tree. Now the second figure you see is actually a spiraling leaf that is formed by changing the orientation of the triangle in the middle. Next, we have the Mandelbrot set. Mandelbrot set is actually one of the important fractal geometries, which was found out by Benoit Mandelbrot. The Mandelbrot set is the set of values of C in the complex plane for which the orbit of the critical point Z is equal to 0 under iteration of the quadratic map Zn is equal to Zn square plus C remains bounded. That is, we take those values of C in which the mode Zn is less than or equal to R. Usually R is taken to be 2, and we can see the Mandelbrot set figure. In this, the real axis, that is the x-axis, ranges from minus 2.25 to 0.75, and the imaginary axis, that is the y-axis, ranges from minus 1.5 to 1.5. The entire figure is embedded in a square of area 9. Now let us go through some applications of fractal geometry. The first application is fractal antenna. In fractal antenna, actually we can use fractals to make antenna such that within the small surface area we can transmit or receive electromagnetic radiation. It does not use up that much of volume or area. That is the use of fractal antenna. Next we have, so we can see the figure of fractal antenna is also given. Next, we have fractal image compression. One of the most useful application of fractals is actually fractal image compression. The basic concept behind fractal image compression is to take an image and express it as an iterated system of function. The basic idea is that a picture views better when it is enlarged. That is, there will be no pixelation. However, it is difficult to do this process because to take an image and express it as an iterated system of function is kind of difficult. Next, I use this in biology. In biology there are various use, that is, for example, we can find the certain biological figure, the shape of or the architect of such certain biological structures can be found out through fractals. Then in medicines, we know there are many ways to scan. There is CT scan, MRI scan, and so on. But it is really time consuming to compare each scans manually and to find out the error. It is really hard. So what we do is uh, we feed with the help of fractals, we feed in the computer the difference between a healthy organ or unhealthy organ with the help of fractals, and the computer itself would give us the information whether it is healthy or unhealthy. Fractals has mainly its use in cancer, in treating cancer as well as in curing it. That is, in cancer, if there is cancer, the blood cells will appear in a tangled form. Uh, Elsewhere, in healthy, blood cells will appear in an organized form. So, with the help of fractal geometry, we can identify a cancerous cell or a healthy cell. Next, we have its use in electrocardiogram. Electrocardiogram is actually a process of recording the electrical activity of a heart over a period of time. Electrocardiogram is done by placing electrodes on the over the heart. In the skin, and then we get a graph, that is amplitude versus time graph, which is actually a depolarization and repolarization graph. With the help of fractal, we can find out whether there is any problem in the heart. uh, so um, so fractal geometry has various uses in our day-to-day life. For some of them, it is just it is nothing more than just beautiful pictures, and for others, they are more complicated figures which can never be studied, or it has many uses in physics, biology, and medicines. It can be also used to study the growth of bacteria and so on. Yeah, that's all. So thank you for hearing out our project.
Thank you, Sita Lakshmi and Ria Thomas. Now let me invite Sidi Media and Viba for their presentation.
Ma'am, may I present?
Yes, Vibha.
Ma'am, is the presentation visible?
Yes, yes.
Good evening, all. Now we have heard about some physical aspects of mathematics, some geometrical aspects of mathematics, and now we are going to talk about biological aspects of mathematics, which is mostly related to the present situation, that is the COVID-19. We were eager to know what are the ways by which these values of deaths, etc., are being calculated. So that's what our project is going to discuss. That is mathematical modeling, which is a tool in most of the science branches. What I mean them is mathematical etymology, from where our project is being taken, that is estimation of the outbreak of universal pandemics.
As the title suggests, we are discussing about estimating the number of deaths, recovered individuals, infected individuals, and even the financial conditions by which these diseases held up. So, before knowing about the present situation, there are few diseases that have taken lives around the globe from the 14th century Black Death to the present century's COVID-19. There are millions of lives that have been taken by these diseases. Now, getting on to know on our project, there are certain terminologies, first of all, to know. That is mathematical modeling. It is a study and analysis of determinants, patterns, and distributions, which describes the health and the disease conditions of our population. Epidemic means the diseases that visits upon a population, examples measles or malaria. Endemic means the diseases that resides within a population, example chickenpox. And pandemic means which affect globally and last for a long time. Example is COVID-19, Spanish flu, etc. And for finding or comparing the methods using mathematics to find how these diseases have been categorized, we use certain compartmental models. At present, there are 8 compartmental models, starting from SIR model to MSEIRS model. So there are 2 types of transmissions, that is vector and vertical transmission. Where vector transmission is, there is a mediator by which the disease is being transferred. Maybe a mosquito in chikungunya or dengue, or in vertical transmission, the disease is transferred from generation or from mother to child, that is HIV or hepatitis B. So moving on to the history of mathematical modeling, mathematical epidemiology gained recognition as a branch when Daniel Bernoulli published his first seminal paper on smallpox. Scientists like Laplace, Goldberg, and Wages forwarded his equation to form the first model, that is compartmental model, which is the simplest model, SIR model. But it was invalid for certain conditions. Ronald Rose, the Nobel Prize winner for his work on malaria, also studied this equation. But it took a leap when Kermack and McKintrick, they proposed their theory on the hypothesis which predicts the number of distribution of infectious individuals over a population over a time, with initial conditions as ds by dt equal to minus lambda s, dou I by dou t plus dou I by dou a equal to delta of a lambda s minus gamma of ai, dr by dt equal to integral 0 to infinity gamma of I of a comma t dA, where delta of a represents Dirac delta function and the infection pressure lambda is being represented using integral 0 to infinity beta of I of a comma t dA. This model is viewed in a single equation as I of t equal to integral 0 to infinity I of a comma t dA. The scientists Kermack and McKintrick described, or they extended the equation using certain conditions such as birth, death, migration rates, and imperfect immunity, as ds by dt equal to b naught plus bss plus bii plus brr minus lambda s minus mss. Dou I by dou t plus dou I by dou a equal to delta of a lambda s plus sigma r minus gamma of ai minus mu of ai, where I of t equal to integral 0 to infinity I of a comma t dA, dr by dt equal to integral 0 to infinity gamma of a I of a comma t dA minus sigma lambda r minus mrr, where b naught represent the migration rate, other b values represent the per capita birth rate, m represent the per capita mortality rate, and mu represent the imperfect immunity. But this model is difficult to analyze in its full generality, and a number of open questions remain against its dynamics. Not only in mathematics, but also in statistics, various models were formed for finding an equation for how we will calculate the number of deaths or recovered individuals, etc. From that in-course probabilistic model and Rydberg stochastic model, we came into a conclusion with a Bernoulli random variable, that is I of t plus 1 equal to summation k equal to 0 st b into 1 minus p raised to it, and st plus 1 equal to st minus it plus 1, where p is a probabilistic value and Beta or B represent the Bernoulli random variable. This equation can be rearranged to it plus 1 equal to st into 1 minus 1 minus p raised to it, and st plus 1 equal to st into 1 minus p raised to it. This is the whole form, how the epidemiology branch was created, or what is the history of mathematical epidemiology. Now moving on to our first topic, that is the compartmental model, which is one of the simplest compartmental model, or which is the used model, or now in the present situation, the COVID-19 model is one of the model that is formed from the SIR model, where S represents the susceptible condition, I represent the infectious condition, R represent the recovered condition. So this model is reasonably predictive for infectious diseases that are transmitted from human to human and where recovery confers lasting resistance, such as measles, mumps, and rubella. There are 5 properties for this model, that is, SIR model is dynamic without vital dynamics, the force of infection, vital dynamics, and constant population, and certain rules how we use this model for proposing for a equation or for a disease. So SIR model is dynamic until there is, like the graph represented here, the susceptible individuals falls rapidly to the compartment, and from where the infected individuals increases, and from there they move to the recovered compartment until there is a backup for this susceptible compartment, that is, new individuals are not being fall into the susceptible compartment, the disease is not said to be outbreak. Now, my friend Simi would explain more about this model.
Am I audible?
Yes, sir.
Yes, you.
The next topic is SIR model without vital dynamics. That is, we are considering a population without vital dynamics like birth rate, death rate, etc. So we have a system of differential equations as dx by dt equal to minus beta si by n, di by dt equal to beta si by n minus gamma I, and dr by dt equal to gamma I. That is, beta is the transmission rate and gamma is the removal rate. And on addition and integration, we get s of t plus I of t plus r of t equal to a constant, that is the population n. Now we are discussing about the basic reproduction number R naught, that is disease, how the rate at which the disease or the bacteria virus reproduces. R naught equal to beta by gamma, that is transmission rate by removal rate. The typical time between the contacts is Tc, which is equal to beta inverse, and the typical time until the removal, Tr, equal to gamma inverse. That is, a infected individual can infect the other people before he gets removed, and that time is Tr equal to gamma inverse. So we get the basic reproduction number as Tr by Tc. Now, by dividing the first differential equation and on integration, we get s of t equal to s of 0 into e raised to minus r naught into r of t minus r of 0 by n, where s of 0 and r of 0 are the initial number of susceptible and recovered individuals. Now, the rate of change of infected individuals in a population, that is di by dt. If di by dt is less than 0, then we say that the population has the disease to be removed, or it attains the disease-free equilibrium. And if di by dt is greater than 0, then the number of infected individuals in a population is increasing. The next topic is force of infection, that is the speed at which the infection can infect the population, and it is represented as f is equal to beta I for a constant population n, f is equal to beta I by n. The SIR model with vital dynamics and constant population. Here we are discussing about the population which is constant, and also we are considering the population with vital dynamics. We are considering the population with birth rate and death rate included. That is, ds by dt equal to lambda minus mu s minus beta si by n, di by dt equal to beta si by n minus gamma I minus mu I, and dr by dt equal to gamma I minus mu r. That is, mu is the death rate for each compartment S, I, and R, and lambda is the birth rate. If R naught, the basic reproduction number R naught is less than or equal to 1, then we say that the population attains disease-free equilibrium. And if R naught is greater than 1, we say that the population has an endemic equilibrium. We have three rules for this SIR model. That is, an infected individual can infect the susceptible individual with a probability lambda. And the second rule is an recovered individual an infected individual can be recovered with a probability delta. And the third rule is a recovered individual can again be infected or can again be susceptible with a probability lambda. Now our next chapter is war with virus. That is, we are discussing the model, mathematical model for coronavirus disease. We have many models, including many compartments or classes for coronavirus models, but we are discussing only about the isolation class model here in this chapter. We'll explain the flowchart with an example. That is, ഒരു ഇൻഫെക്റ്റഡ് ആയിട്ടുള്ള ഇൻഡിവിജ്വൽ, ഇപ്പോൾ സപ്പോസ് എ എന്ന് പറയുന്ന ഒരു ഇൻഫെക്റ്റഡ് ഇൻഡിവിജ്വൽ ഒരു സൂപ്പർ മാർക്കറ്റിൽ കയറുകയാണെങ്കിൽ അവിടെ ആ സമയത്ത് ഉണ്ടായിരുന്ന വ്യക്തികൾ, അല്ലെങ്കിൽ ആ ദിവസത്തിൽ ആ സൂപ്പർ മാർക്കറ്റിൽ ഉണ്ടായിരുന്ന വ്യക്തികളെല്ലാം നമ്മൾ സസെപ്റ്റബിൾ കാറ്റഗറിയിലാണ് ഉൾപ്പെടുത്തുക. ഇനി ആ ഇൻഫെക്റ്റഡ് ആയിട്ടുള്ള വ്യക്തിയായിട്ട് ക്ലോസ് കോണ്ടാക്ട് ആയി വന്ന ആളുകളെ നമ്മൾ എക്സ്പോസ് കാറ്റഗറിയിൽ ഉൾപ്പെടുത്തും. അതായത് അവർ ഇൻഫെക്ഷന് എക്സ്പോസ്ഡ് ആയി എന്ന് പറയാം. സോ that is, if an individual A enters into the susceptible compartment, he removed from the compartment, how he can move to the exposed category. In each compartment, the individual can be removed from the that respective compartment due to death. That is, due to any reasons due to the infection or any other reasons for the death. So he can be removed from the compartment. So when A enters into the susceptible compartment, he gets removed from the compartment with the rate mu s, or he enters into the exposed category with the rate beta s into E plus I. From the exposed compartment, he can be either removed due to death, that is with the rate mu E, or he can be moved to, directly to the quarantine class, or he can be infected and then moved to the quarantine class. So he moves to the quarantine class with the rate gamma E, and that to I, the infected class with the rate pi E. From the compartment I, he can be removed due to death, that is mu I, or he can be quarantined with a rate sigma. From the quarantine class, he can be either recovered or can be removed due to the death. That is, by death, the rate is mu q. To the recovered compartment, the rate is theta q. From the recovered compartment, he can be removed due to the death. That is, we have in coronavirus disease, we have post-COVID symptoms. So due to that also, the disease also, the person can be removed by death. So the rate is mu r. From this, we get a system of differential equations. ds of t by dt equal to a minus mu into s of t minus beta n into s of t into e of t plus I of t. And de by dt is equal to beta n into s of t into e of t plus I of t minus pi e of t minus mu plus gamma e of t. And di of t by dt equal to pi e of t minus sigma I of t minus mu I of t. And dq by dt equal to gamma e of t plus sigma I of t minus theta q minus mu q of t. And dr by dt equal to theta q of t minus mu r of t. Without loss of generality, we can remove the condition of recovered class, since we are only discussing about the isolation class in this chapter. And by substituting n equal to a by mu and capital S by n equal to small s, e equal to e by n, etc., we get the system of equation as ds by dt equal to mu minus mu s minus beta n into s into e plus I, and de by dt equal to beta n into s into e plus I minus pi e into mu plus gamma into E. And di by dt equal to pi E minus sigma I minus mu I, and dq by dt equal to gamma E plus sigma I minus theta q minus mu q. With the initial conditions S of 0 equal to S naught greater than or equal to 0, E of 0 equal to E naught greater than equal to 0, etc. Now we have a lemma and two theorems. That is, first lemma is, under the conditions, all the solution S of t, E of t, I of t, and Q of t of the system, that is the system of equation, remains non-negative for all t greater than or equal to 0. Next is local stability and existence of positive equilibrium point. In this, we say that the system of equation is locally stable. We find out the basic reproduction number using two matrices, that is f is equal to beta n into s into e plus I 0, and v equal to matrix v equal to pi e plus mu plus gamma into e minus pi e plus sigma I plus mu I. We find the Jacobian of these two matrices, and finding out f into v inverse, we take the dominant value as the basic reproduction number r naught, which is equal to beta n into sigma plus mu plus gamma mu plus pi by sigma plus mu plus gamma into sigma plus mu. Now we have a theorem that a system is locally stable related to virus equilibrium point C naught if R naught is less than 1, and if R naught is greater than 1, then it is unstable. That is, if the basic reproduction number is greater than 1, then we say that the system of equations is unstable, and if it is less than 1, then it is stable. The next theorem is the theorem there exists a unique positive virus equilibrium point C star S star, E star, I star, Q star for the system if R naught is greater than 1. That is, if the basic reproduction number is greater than 1, that is, there is an increase in the number of infected individuals. Hence, there is a positive virus equilibrium point in the population. This is all about the chapter 3. And next chapter is the strength and limitations of mathematical models. The main strength is that it helps in this mathematical models helps in different calculations in different branches, like we are discussing about epidemiology in this, and its accuracy could help to prevent and cure and recover the diseases. It can be used in many departments, like for the research, and it can be used for career options in not only in mathematics, in medicine, also in mathematics. And models can also be used locally as well as in local condition, also in global conditions also. The main limitation is time is the main limitation. That is, if the mathematical models cannot be used appropriately in the specified time, then it will cause the death of many people, and the mathematical errors or any inappropriate models can also cause the same, and the delay could affect the economy of the country. This is about a project, and next slide, Vibha will explain the next slide.
So at the present situation, we all know there are vaccines. The government is saying that we will get medicines and other things regarding coronavirus, and we would be once again without mask, etc. But at the present situation, we wish and we have this project done, and we got a great number of deaths that have been occurred by most of the pandemics that have held. And from our point of view, we would say that prevention is always better than cure. And from this part, we have to show you a video and a value of the corona rate throughout the world. The video that we are going to show is how India have reached to the top 5 of the coronavirus affected countries during the whole years or during the whole months that have passed. Simi, is it visible?
Yes, it is visible.
This is how by 2020 month of July, India have taken the place at top 5, and we are still continuing our position there itself, I think. And the other is the value or the total number of corona cases that have been affected around the globe, and the deaths that have taken place around the globe. And also there is a hope that is there are a half number about recovered individuals also from the coronavirus. That's because of the help of our medical team and other people who have helped all the peoples around the world. So that's about the video, and so as always mentioned, prevention is better than cure, and we should stay home, stay safe always. Simi, is the presentation again visible?
Ah, yes, it is visible.
Okay.
Okay, we know that from 1918, in 1918 the globe was affected by Spanish flu, and now here we are in 2021 in the 21st century. The science has developed, the financial status of people have developed, the technology has developed, everything has developed, but the situation remains same as in the earlier time, that is in 1918 Spanish flu. Many of the people have lost their lives due to these diseases like now coronavirus. Many of people have lost their lives. So the question remains open, like how the development of science, how can we improve the by the development of science, the to control the number of death, what can we do? That the question remains open still now, and the answer should be found out by the people like the youth like us, the especially the math students like us. And this is all about our project. Thank you.
Any questions? I think, is there any questions? Nafida, you have any question? No. I think there is no questions, right? That's all on our part, and thank you. That's our project.
Thank you, Simi Maria and Viba. Thank you all for your wonderful presentation. Next is the time to clear the doubt. Anyone can ask if there is a doubt? Next, I invite Anita Peter for the vote of thanks.
A very good evening to all. UG project presentation of Department of Mathematics and Statistics in association with R&D cell has come to a conclusion. Hope that this section was useful and informative. I am assigned the duty of vote of thanks. Without much ado, let me move on to the duty. First, I would like to thank all our dear seniors who has taken a lot of effort to prepare this wonderful presentation for each and every one of us. Thank you, dear seniors. Then I would like to thank our beloved HOD, Miss Aishwarya Paul, and the Department of Mathematics and Statistics, the R&D cell and its active members. Last but not the least, I thank you, my dear friends, for your time today. Once again, I thanks one and all present here. Thank you.
Thank you all. I think we can wind up. Dear seniors, thank you so much for giving away a very inspiring presentation.